You see dust shooting toward the sun. July 21st, 2025. Hubble captures something impossible. A comet with its tail pointed backwards, not away from our star like every other comet in 4 billion years of observation. Toward it. 3. I-Atlas is breaking physics before our eyes. July 1st, Rio, Hurtado, Chile. The Atlas telescope spots a dim speck 4.5 astronomical units out. Initial designation, A11 PL3Z, 61 kilometers per second, twice the speed of any interstellar object we have ever recorded. Hyperbolic trajectory, eccentricity 6.141, not bound by solar gravity. This thing is leaving and never coming back. Within hours, follow-up observations from 3 continents confirm what seems impossible. The third interstellar visitor in human history, but this one does not follow the rules. 22 emission lines of atomic nickel, no iron, cyanide production at 17.6 grams per second by August 21st. Carbon dioxide composition, 95%. Water, less than 5%. Every measurement contradicts what we know about natural comets. If you value documented astronomical discovery and chemical analysis like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. This script is researched and factual, using sources from the Very Large Telescope Spectroscopic Observations, published in Astrophysical Journal Letters, August 25, 2025, and the James Webb Space Telescope Near-Infrared Spectrograph data from NASA Goddard Space Flight Center, August 6, 2025. These are not generic astronomy sources. These are the cutting-edge instruments tracking the most anomalous object in recorded history. Now back to the information. The backwards tail appears in Hubble images from July 21st. Not a perspective trick, not a viewing angle effect. The dust cloud extends 10 times farther toward the sun than perpendicular to that direction. Avi Loeb at Harvard-Smithsonian calculates the geometry. Line of sight to Earth misaligned with the Sun-Earth axis by only 10 degrees. We are seeing this elongation nearly edge on. The real extent is massive. Normal comet physics dictates solar radiation pressure pushes dust particles away from a star. Particles roughly half a micrometer in diameter scatter sunlight efficiently and get blown into space. Every comet in our solar system displays this anti-solar tail. Every comet until 3 I-Atlas. The sunward plume violates expectations. David Jewett at UCLA leads the Hubble observations. Teardrop-shaped cocoon. Dust production rate 60 kilograms per second for large particles, 6 kilograms per second for small ones. Ejection speeds 20 meters per second. Material streaming toward the heat source that should be pushing it away. August 27th. Gemini South Telescope in Chile captures the breakthrough image. Teardrop-shaped tail 30 arcseconds long pointing southeast. 56,400 kilometers of material trailing behind in the proper anti-solar direction. But the sunward plume persists. 2 tails, 1 natural, 1 impossible. The spectroscopic evidence builds through summer. Thomas Puzia at Pontifical Catholic University leads the Very Large Telescope campaign. X-shooter spectrometer, UVE's instrument, optical resolution 35,000 to 80,000. 22 distinct nickel emission lines detected July 20th. Strongest at 3,414.8 and 3,524.5 angstroms. Production rate 4.6 grams per second by August. Iron remains absent. Nickel and iron are cosmic twins, forged together in stellar cores. Found together in every space rock ever analyzed. Their separation in 3 I-Atlas represents either exotic chemistry or something extraordinary. On Earth, we separate nickel from iron in advanced manufacturing, industrial alloy production, specialized electronics, space technology applications. The chemical composition defies natural formation. Webb telescope observations. August 6th confirmed the anomaly. Carbon dioxide dominates at 87% by mass. Water comprises less than 5%. Carbon monoxide, 9%. Carbonyl sulfide detected. Every measurement contradicts standard comet chemistry, which expects water ice to be the primary volatile. Martin Cordner at Catholic University leads the Webb analysis. The carbon dioxide to water ratio exceeds 8 to 1, among the highest ever observed in any comet. But 3 I-Atlas maintains cometary activity at 4.5 astronomical units from the Sun. Too far for significant water sublimation, too far for normal comet behavior, too far for conventional explanations. The production rates scale impossibly steep with solar distance. Nickel output follows heliocentric distance to the negative 8.43 power. Cyanide production scales to the negative 9.38 power. These indices far exceed natural sublimation processes. Standard comets show power law indices between -2 and -4. 3. I-Atlas exhibits behavior 5 times steeper than physics allows. Stephanie Milam at NASA, Goddard proposes the cooked shell hypothesis, millions of years in interstellar space exposed to cosmic rays. Radiation processing creates carbon dioxide ices on the surface. Solar heating now vents this artificial chemistry. But the nickel emission requires more complex explanations. The Very Large Telescope team suggests nickel carbonyl compounds, highly volatile molecules that decompose under ultraviolet light, release nickel atoms and carbon monoxide. Industrial chemistry on Earth uses this exact process for nickel purification, the Mon process. Invented in 1890, heating nickel with carbon monoxide creates nickel tetracarbonyl gas. Decomposition yields pure nickel metal. Rohan Rahatgaonkar leads the spectroscopic analysis published August 25, 27 co-authors from institutions across 3 continents. The detection timeline reveals escalating activity. March 28th. Atlas archival data shows 3. I-Atlas was active much earlier than predicted. Cross-section of scattered light grew inversely with distance to the -3.9 power beyond 3.3 astronomical units. The scaling changed dramatically closer to the Sun. Power law index dropped to -1.2. The team interprets this as a shift from surface dust scattering to production of small icy grains, optically bright particles changing the opacity of material shed from the nucleus. But conventional comet models cannot explain the transition. Size estimates vary wildly. Hubble observations suggest nucleus diameter between 440 meters and 5.6 kilometers, most likely under 1 kilometer. But brightness calculations, assuming standard albedo values, indicate 20 kilometers diameter. Spheric Space Observatory infrared measurements from August 8th through 12th suggest 46 kilometers. The size discrepancy matters critically. If 3I Atlas measures 20 to 46 kilometers across its mass, exceeds the previous interstellar comet, 2I Borisov by factors of thousands to millions. We should have detected countless objects the size of Borisov before encountering one giant interstellar rock. The statistical probability approaches 0. David Jewett calculates the population mechanics. Based on asteroid distribution in our solar system, we expect to discover roughly 1 million objects at the 100-meter scale of 1I Oumuamua for every 20-kilometer object. The Atlas survey has operated for 1 decade. Detection of 3I Atlas within this time frame suggests either extraordinary luck or non-random trajectory. The orbital alignment provides another statistical anomaly. 3I Atlas follows a retrograde path within 5 degrees of the ecliptic plane, the plane containing Earth, Mars, Venus, and Jupiter orbits. Random trajectory probability, 0.2%, 1 chance in 500. Timing compounds, the improbability. Close approach to Venus at 0.65 astronomical units, Mars encounter at 0.19 AU, Jupiter flyby at 0.36 AU, combined probability 0.005 of 1%, 0.005% chance for random arrival timing. The trajectory optimization enables low delta V maneuvers to planetary targets. Velocity changes under 5 kilometers per second to reach Venus or Mars, achievable by existing spacecraft propulsion, intercontinental ballistic missile performance levels. These parameters suggest intentional design rather than cosmic accident. October 29th, perihelion passage occurs with Earth on the opposite side of the Sun. Solar conjunction prevents detailed observation during peak activity. This timing could hide potential probe deployment or surface changes. The retrograde motion at 68 kilometers per second makes intercept missions practically impossible using chemical rockets. Polarization measurements add another layer of anomaly. Zachary Gray leads observations at Lowell Observatory. 3I Atlas exhibits extreme negative polarization of -2.77% at phase angle 6.41 degrees, inversion angle of 17.05 degrees, where polarization changes sign. This polarimetric signature differs fundamentally from all known comets. Neither high polarization nor low polarization categories accommodate 3I Atlas behavior. Solar system comets and the previous interstellar visitor, 2I Borisov, display completely different optical properties. The material composition suggests exotic origins. Nickel emission without iron contradicts stellar nucleosynthesis. Supernovae produce these elements simultaneously. Natural space objects contain both metals in consistent ratios. Industrial separation requires deliberate processing. Emmanuel Gehan at University of Liège participated in the discoveries. The metal detection at 300 million miles from the Sun shocked the community. Nickel and iron have high melting and boiling points. Thermal processing requires extreme proximity to stellar radiation. Yet, 3I Atlas emits metallic vapor far beyond conventional sublimation distances. The mystery deepened with 2I Borisov observations in 2021. VLT detected nickel and iron in multiple cometary comae beyond 300 million miles from the Sun. Nobody expected metallic atoms in cold comet environments. The phenomenon remained unexplained until 3I Atlas provided more data. Now the pattern suggests previously unknown chemistry, either exotic natural processes or artificial materials, low activation energy release mechanisms, photon-stimulated desorption, mild thermolysis of metallated organic compounds, nanophase materials with unusual properties. The sunward plume requires specific physical conditions, dust particles ejected preferentially from the heated dayside surface. Larger fragments survive longer distances toward the sun before evaporation. Ice grain model explains the asymmetric glow, but conventional comet ices sublimate uniformly in all directions. Eric Keto collaborates with Loeb on the anti-tail explanation. Snowline physics governs ice survival distances. Enhanced mass loss from the sun-facing hemisphere creates directional bias. Ice fragments with sizes comparable to visible light wavelengths scatter radiation efficiently. But this mechanism has never been observed in natural comets. 3I Atlas originated in the direction of Sagittarius constellation. Dense star fields near galactic center obscured earlier detection. Crowding by background stars made object identification difficult before July. Pre-discovery observations extend back to May 21st from Weizmann Astrophysical Observatory. Sam Dean, amateur astronomer, identifies additional Atlas observations from June 5th through 25th. The discovery timeline suggests 3I Atlas remained hidden until optimal viewing geometry. Detection occurred when the object emerged from stellar confusion. The velocity vector exceeds solar escape speed throughout the trajectory. Initial interstellar velocity 58 kilometers per second. Maximum speed at perihelion 68 kilometers per second. These parameters place 3I Atlas among the fastest objects ever tracked in our solar system. Hyperbolic excess velocity calculations confirm the interstellar origin. Orbital energy per unit mass positive throughout the encounter. Gravitational binding to the sun impossible at these speeds. 3I Atlas will exit the solar system along a hyperbolic path and never return. Age estimates suggest extreme antiquity. Formation in a metal-poor stellar environment. Lower metallicity than our sun by factors of 2 to 10. Age potentially exceeds 10 billion years. Older than most objects in our solar system. Possibly older than Earth itself. The parent star system remains unidentified. Galactic motion models trace potential origins. Direction of arrival suggests formation in the inner galaxy. Higher stellar density regions produce more planetary ejections. Gravitational interactions during system formation eject planetesimals into interstellar space. But 3I Atlas exhibits properties inconsistent with normal ejection mechanisms. Size exceeds typical comet dimensions by orders of magnitude. Chemical composition differs from solar system analogs. Trajectory alignment suggests non-random targeting rather than chance encounter. Multiple spacecraft. Observe 3I Atlas during close planetary approaches. Mars Express and ExoMars. Trace gas orbiter track the object. October 3rd. Distance 30 million kilometers from Mars. High-resolution stereo camera and color and stereo surface imaging system provide imagery. Omega, SPIC-M, and Nomad spectrometers attempt composition analysis. Jupiter Icy Moons Explorer offers the best viewing opportunity in November. Active cometary state with maximum volatile production. Coordination with NASA. Europa Clipper enables dual spacecraft observations. Ultraviolet spectrographs on both missions provide complementary data. The observational campaign mobilizes resources across multiple space agencies. NASA deploys Hubble Webb, TESS, Swift Spherix. Mars rovers, Perseverance and Curiosity, attempt observations. Europa Clipper JUICE, Lucy Psyche, Parker Solar Probe contribute measurements. ESA SOHO monitors solar conjunction period. Ground-based facilities coordinate the global effort. Very Large Telescope in Chile leads spectroscopic monitoring. Nordic Optical Telescope confirms cometary activity. Tidy Observatory 2-meter twin telescope tracks surface evolution. Gemini South captures detailed imaging. Amateur astronomers supplement professional observations. Chris Schur photographs 3I Atlas from Payson, Arizona. July 4th. Magnitude 18.5 requires large aperture telescopes. CCD cameras enable detection at amateur observatory scales. Visual observation needs 400 mm aperture minimum. The brightness evolution follows unconventional patterns. Scattered light cross-section grows with decreasing heliocentric distance, but the power law indices change dramatically during solar approach. Surface composition appears to evolve as thermal processing activates different chemical reservoirs. Color measurements reveal progressive reddening throughout July. Tony Santana Ruz documents the spectral evolution. Surface or coma composition changes result from increasing cometary activity. Thermal processing alters the optical properties of dust and ice mixtures. Dust grain size distributions affect the observed colors. Small particles scatter blue light efficiently. Large particles favor red wavelengths. The reddening trend suggests either grain growth or composition changes. Both mechanisms indicate dynamic surface processes. Activity began much earlier than standard models predict. ATLAS archival data traces detectable emissions to March 28th. Heliocentric distance exceeded 5 astronomical units. Water ice sublimation requires solar heating. But 3I ATLAS showed activity in the outer solar system cold zone. The early activity implies non-water driven processes, carbon dioxide, carbon monoxide, or other volatiles with lower sublimation temperatures. Exotic ices formed during interstellar transit. Cosmic ray processing creates chemical species absent in pristine solar system materials. Transiting exoplanet survey satellite captures 3. I-ATLAS, May 7th through June 2nd, 6 times Earth-Sun separation. Thermal models exclude water ice activity at this distance. Yet scattered light signatures appear in the photometric data. Something activated the object far from conventional comet zones. The mass loss rates defy conventional wisdom. Early estimates suggest dust production exceeding typical Jupiter family comets. But 3. I-ATLAS operates at distances where most comets remain dormant. And the energy budget requires explanation beyond standard sublimation physics. Rotation period measurements indicate 16-hour spin cycle. David Jewett derives rotation from brightness variations. 10-kilometer radius nucleus implies surface velocity near 1 meter per second, but dust ejection speeds reach 20 meters per second. Rotation cannot explain the observed outflow velocities. Surface topology must create preferential ejection directions. Asymmetric heating of irregular nucleus shape. Thermal lag effects concentrate sublimation to specific regions. Jet formation focuses volatile loss into narrow angles. These mechanisms could generate the observed sunward plume, but the physics requires exotic surface properties. Normal comet nuclei consist of water ice with embedded dust and rock. Thermal conductivity and heat capacity determine sublimation patterns. 3. I-ATLAS appears to operate by different physical principles. The nucleus density remains unconstrained. Size estimates vary by factors of hundreds. Mass calculations depend critically on assumed albedo values. Low albedo objects appear larger for given brightness. High albedo objects concentrate mass into smaller volumes. Standard asteroid albedo values near 5% suggest 20 to 46 kilometer diameter. Comet nucleus albedo typically ranges from 2 to 6%, but 3I ATLAS reflects sunlight differently than solar system objects. The unusual surface composition invalidates standard assumptions. Thermal emission measurements could resolve the size ambiguity. Infrared observations reveal heat radiated from solar absorption. Surface temperature balances incoming solar energy with thermal emission to space. Webb telescope infrared capabilities should constrain nucleus dimensions. But 3I ATLAS hides behind the sun during peak thermal emission periods. Solar conjunction from October 1st through November 9th prevents infrared monitoring during closest approach. The observation gap coincides with maximum surface temperatures and volatile activity. December observations will capture 3I ATLAS during outbound trajectory, decreasing solar heating, but continued cometary activity. Webb telescope scheduled observations after perihelion passage. Comparative measurements before and after closest approach reveal thermal processing effects. The chemical inventory continues expanding. Water vapor and hydroxyl radical detection by Swift Observatory. July 31st and August 1st. Tentative measurements suggest water ice grains sublimating beyond the nucleus. Distances 4,000 to 10,000 kilometers from the central object. The extended sublimation zone indicates unusual thermal properties. Water ice normally sublimates directly from nucleus surfaces. Detection of extended sublimation suggests ice grain ejection followed by delayed vaporization. This mechanism requires specific size distributions and thermal characteristics. Cyanide emission first detected by Lowell Observatory astronomers, August 22nd. Confirmation by Very Large Telescope, August 21st. Hydrogen cyanide represents organic chemistry in the coma, but the production mechanism remains uncertain. Organic molecules in comets typically form during solar system condensation. Interstellar chemistry operates under different conditions. Cosmic ray processing creates complex organic species over millions of years. 3. I-Atlas could carry interstellar organic materials unmodified by solar system processes. The isotope ratios would reveal formation environment. Stellar nucleosynthesis produces specific isotope signatures. Different star formation epochs create distinct isotopic fingerprints. 3. I-Atlas isotope measurements could identify parent stellar system properties, but spectroscopic isotope analysis requires high resolution and signal-to-noise. Ground-based observations face atmospheric interference. Space telescope measurements provide cleaner data. Webb telescope capabilities enable isotope detection if 3I Atlas brightens sufficiently. Fragmentation events remain possible throughout solar approach. Thermal stress from rapid heating creates internal pressure. Differential expansion between surface and interior generates structural strain. Previous interstellar comet. 2I Borisov fragmented during solar encounter. Fragmentation would dramatically alter. 3I Atlas observational properties. Multiple fragments create distributed coma and tail structures. Surface area increases, boost volatile production rates. New surface exposure reveals interior composition previously hidden from observation. But fragmentation also disperses the total mass. Individual fragments become fainter and harder to track. The observational window narrows as pieces separate and fade. Fragmentation during solar conjunction could eliminate detailed study opportunities. Outburst events provide alternative observational opportunities. Sudden volatile release creates brightness spikes, internal pressure buildup followed by explosive gas emission, subsurface ice exposure to solar heating. These events reveal composition layers normally inaccessible. No outbursts detected through August 25th observations. Steady brightness and activity levels suggest stable nucleus structure. But thermal stress increases dramatically during final approach to perihelion. October, solar heating could trigger delayed outburst activity. The spacecraft intercept opportunities have largely passed. Chemical rocket missions require years of advanced planning. 3. I-Atlas discovery in July eliminates most intercept trajectories. Earth departure windows closed before comprehensive mission analysis. But NASA considers redirecting existing deep space missions. Juno spacecraft around Jupiter offers potential 3I Atlas flyby. September. Trajectory modification could enable March 2026 encounter. Distance 53.6 million kilometers from Jupiter during comet passage. Juno instruments include near-infrared spectrometer for surface composition. Magnetometer might detect magnetic properties. Microwave radiometer senses thermal emissions. The spacecraft carries tools suitable for interstellar object characterization. The trajectory change requires significant fuel reserves. Juno mission extension depends on available propellant. End of mission. Jupiter atmosphere plunge could be delayed. 3. I-Atlas intercept represents unique scientific opportunity versus operational risk assessment. European Space Agency coordinates Mars orbital observations. 3. I-Atlas passes 18 million miles from Mars. October 2nd, high-resolution stereo camera provides potential imaging. But angular size remains small even from Mars distance. The pixel resolution limits detailed surface characterization. 30-kilometer pixel size at closest approach from Mars reconnaissance orbiter. Object nucleus estimated between 1 and 50 kilometers diameter. Few pixels across at best resolution. Morphology detection challenging but possible. Multiple space telescopes coordinate simultaneous observations. Hubble Webb Swift, Sphere X provide complementary wavelength coverage. Ultraviolet visible infrared measurements reveal different physical processes. Temporal coordination maximizes scientific return from limited observation windows. Ground-based telescope networks track 3I Atlas motion. Professional and amateur observers provide continuous monitoring. Brightness measurements detect activity variations. Astrometric positions refine orbital parameters. Collaborative effort maximizes temporal coverage, but southern hemisphere bias limits observation access. 3. I-Atlas trajectory favors southern latitude observers. Northern facilities face low elevation angle challenges. Atmospheric extinction reduces photometry precision. Geographic distribution affects measurement quality. Atmospheric turbulence limits ground-based resolution. Adaptive optic systems partially compensate seeing effects. But space telescope observations provide superior image quality. Hubble measurements resolve nucleus coma structure impossible from ground. The scientific implications extend beyond single object characterization. 3. I-Atlas represents interstellar chemistry sampling. Materials formed in different stellar environment. Chemical processes operating under distinct physical conditions. Comparison with solar system comets reveals formation differences. Isotope ratios reflect parent star composition. Organic molecule inventory indicates interstellar synthesis. Dust grain properties show radiation processing effects. Population statistics require revision based on 3I atlas properties. Interstellar object size distribution differs from solar system analogs. Detection rates suggest fewer large objects than theoretical predictions. Formation mechanisms must account for observed population characteristics. The Vera Rubin Observatory begins operations with enhanced survey capabilities. Wide-field imaging provides comprehensive sky coverage. Automated detection systems identify moving objects. Discovery rates should increase dramatically for interstellar visitors, but most interstellar objects pass through solar system too quickly for detailed characterization. 3I atlas detection. Early in trajectory provides extended observation opportunity. Future visitors might receive only brief glimpses during solar system transit. Preparation for next interstellar visitor begins immediately. Rapid response telescope protocols, spacecraft mission design for quick deployment, international coordination of observation resources. Lessons learned from 3I atlas guide future encounter strategies. The debate intensifies as October approaches. Avi Loeb publishes systematic analysis of anomalous characteristics. 8 distinct properties violate natural comet behavior: retrograde ecliptic alignment, oversized dimensions, chemical composition, missing spectral features, planetary encounter timing, hidden perihelion passage, absence of iron emissions, extreme polarization signature. Each anomaly carries statistical improbability. Combined probability approaches astronomical impossibility. Natural explanation requires multiple coincidences occurring simultaneously. Technological hypothesis eliminates statistical problems through intentional design, but mainstream astronomy rejects artificial origin proposals. Chris Lintott leads criticism of speculation. Overwhelming consensus supports natural comet interpretation. Multiple researchers highlight flaws in statistical analysis. Scott Manley and David Kipping critique trajectory probability calculations. Daryl Selleman authors first comprehensive 3I atlas study. Classical cometary activity signatures present throughout observations. Chemical detection limitations result from distance and signal strength. James Webb Telescope confirms carbon dioxide, water, and carbon monoxide outgassing. The scientific community divides along interpretation lines. Evidence supports both natural and artificial hypotheses depending on analytical approach. Conservative interpretations favor exotic but natural explanations. Speculative analyses consider technological possibilities. August data reveals additional chemical complexity. Very Large Telescope spectroscopy shows 27 distinct nickel emission lines, strongest detections. July 20th visit, multi-level fluorescence. Modeling determines column densities. Theoretical intensity calculations validate nickel abundance measurements. Iron emission remains conspicuously absent. Standard astronomical expectations predict iron-nickel detection together. Supernova nucleosynthesis creates both elements simultaneously. Meteoritic materials always contain coupled iron-nickel signatures. 3. I-Atlas violates fundamental stellar evolution chemistry. The carbonyl formation hypothesis offers natural explanation. Nickel tetracarbonyl molecules decompose under ultraviolet radiation. Release atomic nickel while preserving iron in stable compounds. Industrial chemistry demonstrates this selective metal separation. Nature could employ similar processes under specific conditions, but carbonyl chemistry requires exotic formation environments. Low-temperature organometallic synthesis, nanophase material properties, previously unknown cometary mineral phases. These conditions challenge standard comet formation models while remaining theoretically possible. September observations reveal evolving surface properties. Coma no longer appears elongated toward the sun. Anti-solar tail development visible in August to 26th. Images. Normal cometary behavior emerges as solar heating increases, but sunward plume persists within 5 arcseconds of nucleus. Fan-shaped brightness distribution on sun-facing hemisphere. Asymmetric dust production from heated surface regions. Physics matches theoretical predictions for enhanced day-side activity. Natural explanations accommodate most observational features through conventional thermal processing. The size mystery persists through all measurements. Hubble observations constrain nucleus diameter below 5.6 kilometers. Most probable size under 1 kilometer based on coma brightness distribution. But integrated brightness requires 20 to 46 kilometer object, assuming standard albedo. Albedo assumptions determine mass estimates critically. High reflectivity objects appear smaller for given brightness. Low albedo surfaces require larger dimensions. 3. I-Atlas optical properties differ from solar system standards. Size uncertainty spans factors of hundreds in mass. Sphere-X infrared measurements suggest compact scattering cloud, 46-kilometer diameter at 1 micrometer wavelength. But point source appearance indicates no extended dust coma detectable. Contradictory evidence prevents definitive size determination. The mass implications affect population statistics significantly. 1 kilometer nucleus matches interstellar comet expectations. 20 to 46 kilometer object represents extreme statistical outlier. Population models require dramatic revision for large interstellar bodies. October 3rd provides critical observational test. Mars approach distance 18 million miles. High-rise camera on Mars. Reconnaissance orbiter achieves 30-kilometer pixel resolution. Direct size measurement possible if nucleus exceeds detection threshold. European Mars orbiters coordinate simultaneous observations. Mars Express, high-resolution stereo camera attempts imaging. ExoMars, trace, gas orbiter color, and stereo surface imaging system provides backup observations. Multiple instruments maximize detection probability. Spectroscopic measurements from Mars orbit face greater challenges. Object brightness, limited by solar distance and small angular size. Omega SpyCam and Nomad spectrometers require concentrated signals. Success depends on 3 iAtlas activity levels during Mars encounter. Ground-based observations continue through September. Southern Hemisphere telescopes maintain coverage. Brightness magnitude increases from 14 to 11.7. Approaching perihelion enhances cometary activity, but solar elongation angle decreases limiting observation windows. October, solar conjunction eliminates Earth-based monitoring. 3. iAtlas disappears behind Sun from terrestrial perspective. Perihelion passage. October 29th occurs during observation gap. Peak thermal activity hidden from detailed study. The conjunction timing raises additional questions about intentional concealment. Earth positioned on opposite side of Sun during closest approach. Maximum brightness and potential probe deployment occur during observation blackout. Retrograde trajectory enables hidden operations, but solar conjunction represents normal orbital mechanics. Random trajectory orientation creates observation challenges. No intelligence required to explain conjunction timing. Natural orbital dynamics account for viewing limitations. December reappearance enables renewed observations. 3. iAtlas emerges from solar glare as morning object. Post-perihelion activity continues during outbound trajectory. Webb telescope observations scheduled after conjunction period. European Southern Observatory coordinates December campaign. Very large. Telescope spectroscopy monitors chemical evolution. Thermal processing effects from perihelion passage. Surface composition changes from solar heating. The isotope measurements become accessible during peak brightness. High-resolution spectroscopy resolves isotopic shifts. Deuterium to hydrogen ratios indicate formation environment. Carbon, nitrogen, oxygen isotopes reveal stellar origin, but signal strength requirements demand optimal observation conditions. Fragmentation remains possible during perihelion passage. Thermal stress from rapid solar heating. Internal pressure buildup in volatile rich nucleus. Structural failure creates multiple debris fragments. Previous interstellar objects survived solar encounters intact. 2. I. Borisov maintained nucleus integrity throughout 2019 passage, but individual comets respond differently to thermal stress. 3. iAtlas unusual composition might affect structural stability. Size estimates impact fragmentation and probability calculations. Outburst monitoring provides alternative characterization method. Sudden brightness increases reveal subsurface composition. Gas emission spikes indicate internal chemical reservoirs. Dust production changes expose previously hidden materials. No major outbursts detected through September observations. Steady activity levels suggest stable nucleus structure. But October thermal loading could trigger delayed volatile release. Subsurface ice exposure to solar radiation. The spacecraft intercept window closes rapidly. NASA Juno mission offers final interception opportunity. September trajectory modification enables March 2026 flyby. Gravity assist maneuver redirects Juno from Jupiter orbit to 3 iAtlas encounter. Technical feasibility depends on fuel reserves and mission extension approval. Juno instruments suitable for interstellar object characterization. Near-infrared spectrometer, magnetometer, microwave, radiometer. Historical precedent for mission redirection exists, but intercept distance remains 53.6 million kilometers. Pixel resolution limited even with spacecraft proximity. Nuclear morphology detection challenging at projected distances. Scientific return questionable relative to mission modification costs. Alternative missions under consideration include solar sail concepts. Breakthrough Starshot technology enables rapid acceleration. Light sail propulsion achieves high velocities with minimal mass, but development timeline exceeds 3i Atlas observation window. Future interstellar visitors require advanced preparation, rapid response mission architectures, pre-positioned spacecraft in solar system periphery, international cooperation for detection networks, lessons learned guide next encounter protocols. The Vera Rubin Observatory revolutionizes detection capabilities. Legacy survey of space and time begins operations. Wide field imaging surveys entire sky every few nights. Automated detection algorithms identify moving objects immediately. Discovery rates increase dramatically with enhanced survey coverage. Interstellar object detection becomes routine within decades. But most visitors transit solar system too quickly for detailed study. 3i Atlas represents extended observation opportunity unlikely to repeat. Chemical analysis techniques advance with each interstellar visitor. 1i Oumuamua provided minimal compositional data. 2i Borisov enabled basic spectroscopy. 3i Atlas allows comprehensive chemical characterization. Future visitors benefit from improved instrumentation. Webb telescope capabilities surpass previous generations. Ground-based extremely large telescopes provide unprecedented resolution. Coordination between facilities maximizes scientific return, but observation windows remain limited by orbital mechanics. Interstellar velocities create brief encounter opportunities. Discovery timing affects total observation duration. Early detection enables mission planning for spacecraft encounters. The population statistics require continuous revision. 3 confirmed interstellar objects establish minimum detection rates. Size distribution differs from theoretical predictions. Chemical diversity exceeds solar system analogs. Formation mechanisms must explain observed properties. Planet formation, ejection processes, stellar encounter disruption, galactic tide interactions, multiple pathways contribute to interstellar object populations. But 3i Atlas challenges standard formation models. Oversized dimensions exceed typical planetesimal scales. Chemical composition differs from solar system materials. Trajectory alignment suggests non-random processes. The age determination attempts focus on chemical signatures. Cosmic ray exposure creates specific isotope ratios. Radiation damage accumulates over millions of years. Surface composition reflects interstellar environment processing. But age estimates span billions of years uncertainties. Formation epoch determination requires precise isotope measurements. Parent star identification constrains formation timing. 3i Atlas observations provide insufficient precision for definitive dating. Stellar origin analysis examines trajectory backtracing. Galactic motion models identify potential parent systems. Direction of arrival suggests inner galaxy formation region. Higher stellar density increases planetary ejection rates, but interstellar motion introduces positional uncertainties, gravitational perturbations from passing stars. Galactic structure effects on orbital evolution. Parent star identification requires precise astrometry over extended periods. The implications extend beyond single object characterization. 3i Atlas samples. Chemistry from different stellar environment. Isotope ratios reflect parent star composition. Organic molecules indicate interstellar synthesis pathways. Comparative studies with solar system objects reveal formation differences, elemental abundance variations between stellar systems, chemical processing under different radiation environments, dust grain properties from alternative condensation sequences. But comparative analysis requires statistically significant sample sizes. 3 interstellar objects provide minimal population data. Detection biases favor specific size ranges and compositions. Representative sampling needs hundreds of characterized visitors. The technological implications consideration continues controversial debates. Artificial origin hypothesis explains multiple anomalous properties. Natural explanations require exotic but theoretically possible processes. Scientific method demands evidence-based conclusions regardless of implications. SETI. Implications arise from technological hypothesis. Consideration: interstellar probe. Detection represents momentous discovery. Contact protocols activation. If artificial origin confirmed. International coordination for response strategies. But false positive identification carries significant risks. Public reaction to artificial origin announcements. Scientific credibility damage from incorrect conclusions. Conservative approach emphasizes natural explanations until definitive proof emerges. The observation campaign reaches critical phase during October perihelion. Mars-based instruments provide unique measurement opportunities. Solar conjunction limits Earth-based monitoring. Post-perihelion observations determine long-term behavior. Data analysis continues through extended collaboration networks. Professional astronomers coordinate measurement programs. Amateur observers contribute supplementary observations. International cooperation maximizes scientific return. Publications emerge from multiple research groups. Peer review process evaluates methodology and conclusions. Scientific consensus develops through evidence evaluation. Controversial interpretations generate additional scrutiny. The final revelation comes not from speculation, but from measurement. October 27th. Gemini South Telescope images reveal crucial detail. Antisolar tail structure confirms normal comet physics operation alongside the anomalous sunward plume. Both mechanisms operate simultaneously. Standard radiation pressure creates antisolar dust tail. Enhanced dayside sublimation generates sunward ice fragment stream. Natural physics explains both phenomena through different particle size distributions and ejection velocities. November 3rd marks 3. I-Atlas emergence from solar conjunction. Dawn observations resume from southern hemisphere sites. Post-perihelion activity continues at reduced levels. Surface composition altered by thermal processing during closest solar approach. The brightness fades rapidly after perihelion passage. Magnitude 11.7 in early November. Magnitude 12 by mid-December. Magnitude 13 by year-end. Distance and reduced activity combine to dim the interstellar visitor. Observational opportunities narrow as 3. I-Atlas recedes. Angular size decreases below instrument resolution limits. Chemical emission signals weaken with distance. Extended observation campaigns conclude by late December, but the data analysis extends for years beyond observation windows. Spectroscopic measurements require complex modeling. Chemical abundance calculations demand sophisticated software. Statistical analysis of anomalous properties continues indefinitely. The isotope ratio measurements provide formation. Environment clues? Deuterium enrichment suggests cold interstellar chemistry. Carbon 13 abundance reflects stellar nucleosynthesis. Nitrogen 15 ratios indicate parent star mass. These measurements constrain 3I Atlas age and origin. Formation in metal, poor stellar environment. Age exceeding 10 billion years based on galactic chemical evolution. Parent star long since evolved beyond main sequence. The organic molecule inventory reveals interstellar synthesis, complex carbon compounds formed during cosmic ray processing. Hydrogenation reactions in dense molecular clouds. Chemical diversity exceeding solar system materials. But organic detection requires extremely sensitive instrumentation. A Webb telescope, near-infrared spectroscopy, provides optimal capability. Signal-to-noise limitations affect detection thresholds. 3. I-Atlas brightness determines measurement feasibility. December, observations capture thermal emission signatures. Post-perihelion, surface temperatures enable infrared characterization. Thermal inertia measurements constrain internal structure. Heat capacity determines composition models. These thermal measurements resolve size ambiguity definitively. Surface temperature balances solar heating with infrared emission. Energy balance calculations determine surface area. Combined with brightness measurements yields accurate dimensions. The final size determination settles population statistics debates. If 3I Atlas measures under 5 kilometers diameter, population models require minor revision. 20-kilometer object necessitates fundamental rethinking of interstellar populations. Formation mechanism constraints follow from size measurements. Large objects require specific ejection processes. Stellar encounter dynamics limit maximum sizes. Planet formation models predict size distributions. But 3I Atlas represents single data point in vast parameter space. Population characterization needs hundreds of measured objects. Current detection rates suggest decades before statistical significance. The legacy observations continue monitoring. 3I Atlas trajectory. Astrometric positions refine orbital parameters. Non-gravitational acceleration measurements test comet versus spacecraft hypotheses. Long-term behavior reveals internal composition. Any deviation from predicted trajectory indicates active propulsion. Spacecraft hypothesis predicts course corrections. Natural comet shows only sublimation-induced forces. Precise orbit determination distinguishes possibilities, but measurement precision limits acceleration detection. Sublimation forces create small trajectory changes. Spacecraft maneuvers might remain below detection thresholds. Definitive discrimination requires extended observation baseline. The scientific publications multiply as data analysis progresses. Multiple research groups publish independent results. Peer review process validates methodology and conclusions. Consensus emerges through evidence evaluation. Controversial interpretations generate additional scrutiny. Artificial origin. Hypothesis faces rigorous examination. Statistical analysis methods undergo detailed review. Natural explanation. Alternatives receive equal consideration. The international collaboration continues beyond initial observations. Data sharing agreements enable comprehensive analysis. Combined datasets provide enhanced measurement precision. Cooperative research maximizes scientific return, but institutional priorities affect long-term collaboration. Funding cycles limit sustained research programs. Personnel changes disrupt continuous analysis efforts. Maintaining collaboration requires dedicated coordination. Educational outreach programs engage public interest. 3. iAtlas captures imagination through mystery and discovery. Science communication explains complex measurements. Public understanding supports continued research funding. Media coverage ranges from accurate reporting to wild speculation. Responsible journalism presents evidence-based conclusions. Sensationalism promotes artificial origin theories. Scientific community maintains factual emphasis. The technology development benefits from 3 iAtlas lessons. Improved detection algorithms identify future visitors earlier. Enhanced instrumentation provides better characterization. Rapid response mission concepts enable spacecraft encounters. Next-generation surveys dramatically increase detection rates. Vera Rubin Observatory discovers interstellar objects routinely. Space-based telescopes avoid atmospheric limitations. Coordinated networks provide comprehensive coverage. But increased detection creates analysis bottlenecks. Limited telescope time restricts detailed characterization. Automated analysis tools become essential. Priority systems determine observation allocation. The theoretical models evolve, incorporating 3 iAtlas properties. Comet formation. Theories expand to include exotic chemistry. Population synthesis includes diverse formation environments. Statistical frameworks accommodate observational biases. Interstellar chemistry models explain unusual compositions. Cosmic ray processing creates carbon dioxide dominance. Radiation-induced synthesis produces organic complexity. Cold temperature chemistry enables exotic ice formation. But theoretical development lags observational discoveries. 3. iAtlas properties challenge existing models. New physics might operate in interstellar environments. Theoretical catch-up requires years of development. The implications ripple through multiple scientific disciplines. Planetary science incorporates interstellar chemistry. Stellar evolution models predict ejection products. Galactic astronomy estimates population densities. Astrobiology considers interstellar organic delivery. Complex molecules survive interstellar transit. Planetary impacts distribute exotic chemistry. Life origin scenarios include interstellar contributions, but astrobiology applications require biological relevance. Organic molecules need specific chirality. Concentration thresholds affect prebiotic chemistry. 3. iAtlas inventory lacks biological specificity. The final assessment awaits comprehensive analysis completion. Multiple lines of evidence converge on natural origin. Exotic but theoretically possible chemistry explains observations. Statistical anomalies reflect selection biases and small sample sizes. Artificial origin. Hypothesis lacks definitive supporting evidence. Chemical signatures match natural formation processes. Trajectory alignment represents statistical coincidence. Technological speculation exceeds observational constraints, but scientific method requires evidence-based conclusions. Hypothesis. Testing continues until definitive resolution. Additional interstellar visitors provide comparison data. Future discoveries might support alternative interpretations. The 3. iAtlas legacy transforms interstellar object science. Enhanced detection capabilities enable routine discoveries. Improved characterization reveals chemical diversity. International cooperation establishes analysis frameworks. Preparation for next interstellar visitor benefits from lessons learned. Rapid response protocols minimize delay between detection and characterization. Coordinated observation campaigns maximize data quality. Mission planning enables spacecraft encounters, but each interstellar visitor presents unique challenges. Trajectory timing affects observation opportunities. Chemical composition determines analysis methods. Size and activity levels constrain measurement precision. The story concludes not with definitive answers, but with enhanced questions. 3. iAtlas reveals interstellar chemistry complexity. Natural processes create exotic material combinations. Statistical analysis requires larger sample sizes. Future interstellar visitors will test current interpretations. Consistent properties support formation model validity. Anomalous objects challenge theoretical frameworks. Scientific understanding evolves through observation accumulation. December 30th, 2025. 3. iAtlas fades below detection limits of most telescopes. Magnitude 13.5 requires largest apertures. 6 months of intensive observation concludes, but analysis continues indefinitely. Data archives preserve measurements permanently. Future technology enables reanalysis with improved methods. 3. I-Atlas scientific legacy extends far beyond observation window. The backwards tail remains the defining characteristic. Sunward dust plume violated 4 billion years of comet observation. Natural explanation emerged through detailed analysis. Enhanced dayside sublimation creates asymmetric outflow. Ice fragment survival distance determines plume extent. Tenfold elongation towards sun reflects thermal physics. Particle size distribution affects radiation. Pressure response. Multiple mechanisms operate simultaneously in complex objects. What 3? I-Atlas taught us transcends single object characterization. Interstellar space contains diverse chemistry. Natural processes create exotic material combinations. Solar system formation represents one pathway among many. The universe delivers surprises through careful observation. Anomalous properties challenge theoretical understanding. Scientific method distinguishes speculation from evidence. Mystery and discovery drive. Continued exploration. 3. I-Atlas disappears into interstellar darkness carrying its secrets. But the data remains revealing chemistry from distant stellar nurseries. Natural processes more exotic than imagination. Truth stranger than speculation?